simply the executive summary delivered to the entire company at once. A second highly influential computational theory approaches the problem from a different, more philosophical angle. This is integrated information theory, or IIT. Instead of asking what consciousness, IIT starts by asking what consciousness. It identifies the essential properties of our own subjective experience. Every moment of consciousness is rich with detail. And yet it is experienced as a seamless, unified whole. You don't experience the color red separately from the shape of a ball. You experience a unified red ball. IIT proposes that any physical system that possesses these twin properties of information and integration must, by definition, be conscious. To formalize this, IIT introduces a mathematical measure called phi, or F. Phi quantifies the degree to which a system as a whole is more than the sum of its parts. A system with high phi is one where its components are so densely and cleverly interconnected that you cannot understand the state of the system by looking at its parts in isolation. The brain, with its massive interconnectivity, is a prime candidate for a high phi system. In contrast, a system like a digital camera sensor has millions of pixels, but each one is largely independent. Its phi value would be very low. For IIT, consciousness is not an all-or-nothing affair. It's a gradient. The higher a system's phi, the more conscious it is. This provides a powerful, if abstract, framework. It suggests we could, in theory, build a consciousness meter that could measure the phi of any system: a human brain, a cat's brain, a smartphone, or even the internet, and assign it a value corresponding to its level of experience. Like GNW, IIT is fundamentally substrate independent. It doesn't care about quantum mechanics or special biological properties. It cares only about the causal structure of the system, the fabric of cause and effect woven by its interconnected components. If a silicon-based AI could be built with a sufficiently high phi value, IIT would state that it is undeniably conscious, possessing its own genuine inner experience. The implications are staggering. IIT suggests that consciousness might be a far more widespread property of the universe than we typically assume. Any system with the right kind of integrated information structure would have some degree of experience, however minimal. This theory grounds consciousness in the mathematics of cause and effect structures, turning it from an elusive philosophical mystery into a quantifiable physical property. It defines the problem with beautiful precision. Offering a clear computational target to build a conscious machine, we must build a machine with a high value of phi. The challenge is purely one of engineering the right information architecture. Both the global neuronal workspace and integrated information theory are masterpieces of scientific reasoning, providing compelling, testable frameworks for understanding the mind. They represent the intellectual summit of the computationalist viewpoint. Yet, for all their differences in approach, one focusing on function, the other on structure, they are built upon a shared foundational assumption. This assumption is that the classical laws of physics are sufficient. They model neurons as nodes in a network that are either on or off, firing or not firing, and communicating via signals that follow predictable, deterministic paths. In this world, there is no room for fundamental randomness or quantum ambiguity. This assumption is perfectly reasonable.